Section 14.1 is going to continue our discussion of what we started in class with that hands-on activity of the metric system and linear measure. So we aren't going to focus only on the metric system in this section, but we are going to talk about the metric system again. We'll be moving quickly through that one since we've already spent a day talking about it. But we're also going to talk about the English system or the standard system as well. So first, what do I mean by linear measure? Linear measure refers to measuring in a straight line, the same way you would with a ruler. Okay, and you guys did that when you did your activity last time, right? Nobody was measuring the length of the classroom by going like this with your ruler, right? It was straight to the very back of the room. Nobody measured your height except for in a straight line. Some things to remember about measurement is that distance is never negative. If you take the distance from A to B, it's the same as the distance from B to A. And there are two primary measurement systems. One is called the English system. It's not the only thing it's called. Sometimes it's called the standard system. So when you guys take like your OSAT, when you get to that point and you're taking like the math portion of that and so forth, they may use a different language for that. But English or general or standard are sometimes used for those. Customary, sometimes you hear the word customary. I don't know why, but they use that one sometimes too. And then the other one, of course, is metric that we did the activity for in class. So we're going to talk about the English system first. These measurements, at least the first two, I'm sure you know. A foot is 12 inches and a yard is 3 feet. The next one you may or may not know. A mile is 1,760 yards or 5,280 feet. Okay, and the places where I have blanks for you is the language for the units. So feet is FT or foot, yard YD, and mile is MI. Please be careful on mile. Don't put M because that's meters. Okay. The other two you're probably not going to get confused with anything, but miles you could. Now, I mentioned last time that the absolute best thing about the metric system was it's easy to convert, right? And I said, we'll show you why very soon. Well, today is the very soon. We're going to show you why it's so much nicer to convert in metric than it is in the standard English system. So, what we're going to do is we're going to do what's called a dimensional analysis. So there's quite the vocab word for you today, so you can sound very impressive. What did you do in math class today? Dimensional analysis, and they'll be like, whoa, that sounds like scary. Okay, so let me show you what it means. We're going to write down our 72 feet, kind of in a fractional form. So if you want to write it over 1, you can, but you don't have to. What we're going to do next is we're going to multiply by a fraction. That's why I said you could write it as a fractional form. The fraction we're going to multiply is the fraction that changes feet to inches. So I want feet to be on bottom, and the reason I want it there is because then I notice that my feet by the 72 and my feet that are in the denominator will cancel. Okay, so like this piece, whoops, hang on, let me try that one more time. Here we go. This feet and that feet are going to cancel out if I do this right. Okay, that's my goal here. Now I'm going to put feet on bottom, I'm going to put inches on top, and then I want to use the ratio from back here that relates feet to inches. So in particular, we know that 1 foot is 12 inches.
Are we converting it to yards?
Oh, I'm sorry. My bad. Thank you. We'll do yards since it said so. Just for Catherine. Yes, yards. Sorry. Thank you. Okay. Feet to yards. So the feet is 3 feet in 1 yard. The beauty of dimensional analysis is that you don't have to ever try and remember, do I divide by 3, do I multiply by 3? Do I divide by 12, do I multiply by 12? And as we continue through this process, the next one, number 3 in particular, is going to have a 2-step dimensional analysis, and that's where things get harder to remember. Do I divide, do I multiply? Okay, I don't have to remember. I just set up the ratio where feet are on bottom because I want them to cancel, and then I put the numbers in the appropriate place. Now what you see happen here, of course, is yards is what's left, and the numbers are exactly what you expect. So if I'd write this over 1, we see that we have 72 times 1, that's 72 on top. And we have 1 times 3, that's 3 on bottom. And then we actually do that division. Feel free to grab your calculator. What is 72 divided by 3? It is 24, and the correct unit is yards. And those units are super important in this section because that's the whole point. We're changing them. So make sure all of your answers have units on them. Okay, to 24 yards. Any questions on that one? A 1-step dimensional analysis. Did you? Yes. Physics, you'll see it done also in chemistry sometimes. I don't know if you've guys done this in chemistry. I remember doing it in chemistry in high school, doing dimensional analysis, and I remember doing it in physics as well, yeah. It keeps all of our units straight, and that's the beauty of it. All right, this one is changing yards, 89.23 yards into miles. So I need yards on bottom to cancel, miles on top. There is a relationship between yards and miles. What does it say on that previous slide or right above in the box on your paper?
1,760 yards make 1 mile.
Right. 1,760 yards, so that's going to go by yards. 1 mile is what goes on top. So again, the whole point was that the yards cancel. And then we're actually going to take the 89.23 and we're going to divide by 1760. You don't necessarily have to show this fraction. You can just do it if you're okay with that. And this will be miles. So as we're working with this, we're just going to use 2 decimals of accuracy for things. So if we need to round, we're going to round to 2 decimals, okay? What do you get when you round this? And you will need to, because I'm going to write an approximation because we're going to need to do that. If I round this to 2 decimals, what do I get? 5.07 miles. Okay, another one-step dimensional analysis. The next one, not so much a one-step. I've got miles on the left and I've got inches on the right, and if you'll look back in that box, there is no correspondence directly between miles and inches, right? So we're going to have to go through more than one step in order to do that. Now, if I take a look, I do have to do a multiplication where I've got miles in it, otherwise the miles won't cancel. And I have 2 choices. I can do miles into yards or miles into feet, because those are the 2 relationships that I have in that chart. Which one would you like to do? Feet. Okay, so Lexi, I heard you said feet. What's the relationship between miles and feet from that chart?
5,280 feet is 1 mile.
Okay, 5,280 feet is 1 mile. Now I could multiply the 37, the 5,280. The problem is that didn't give me the answer that I'm actually asked to find yet. I'm not asked to find feet. So I'm going to have to do another fraction that eliminates the feet. And can I eliminate feet and turn it into inches with the relationships that I've already established? I can. What is the relationship between inches and feet? 12 inches to 1 foot. And if you'll notice, again, the whole point is that the miles cancel here. Okay, you can't hardly see that black. I don't know why I'm using it. Let me try a different color. How about this one? And thicker, that would help too. Okay, miles cancel here. Feet cancel here, right? So I'm in inches now, right? Because I've canceled out corresponding units the way I needed to. The only thing that's left to do is to multiply. And this one, actually, the denominator is just 1. So all I have is the multiplication. So I have 37 times 5,280 times 12. What in the world does that give me? 2,344,320 inches. And I don't actually think that that's going to fit on your line. I think I didn't get the line quite long enough, but it's okay. You didn't really need the line anyway, did you? Not really. Okay. So, who appreciates the metric system where all we ever have to do is move decimals? I do. Moving decimals is, not that I can't do this, not that you can't do this, but this is more work. Agreed? This is a lot more work, and especially that second one, or the third one down here where we had to do it twice. That's a lot more work than just moving decimals left and right. Okay, so let's take a look a little bit more then at that metric system. So a little bit that I didn't go over last time. The international measurements are usually done in the metric system, especially in science and industry. So sometimes you'll see the metric system written as SI for science and industry. Okay. Multiples or fractions of base units are given by powers of 10. We saw that last time. And the prefixes correspond to various multiples and fractions for all types of units. Okay, the last chart that I showed you did not have the same number in all the places, right? But the beauty of the metric system is it's all based on the number system, base 10. And that's the wonderful thing about it. So what I'm going to do is I'm going to have you fill in a chart. You've seen this chart before, so this is old news. But you're going to fill in all the symbols for the different ones. You'll notice the starred ones. We talked about that last time. Those starred ones are the ones that are commonly used. Not that you can't see the other ones, they just aren't used commonly. And then the factor is written on the right-hand side. And it's a factor based on the base unit. So it's 10 times bigger, it's 1,000 times bigger, or it's 0.1, quote-unquote, times bigger than the base unit. Now you'll notice it just says K, H, D, A, D, C, M, and doesn't say, and usually we see two letters there, right? Like centimeters, cm. This is what can be used for any of those three basic measurements in the metric system. So we had length, that's what we did last time in class, all in meters, right? So centimeters, kilometers, everything in meters. When we do our capacity section, we're going to talk about grams and liters. Those are our other two. So those are the three basic types. So we can put a G for grams, an M for meters, or an L for liters after each one of these, and then we'll actually have the whole unit. These are just the prefixes of whatever unit we're working on. So just for fun and for practice, we're going to do it with meters. This looks exactly like the last one, right? Except it says KM and HM, so forth, all the way down. And it has the relationship to the base unit. So a 1 kilometer is 1,000 meters. 1 hectometer is 100 meters, and so forth. And again, kilometers, meters, centimeters, and millimeters are starred because those are the commonly used measurements. Now, one of the things that you were supposed to have gained from your experiment last time in class was some sort of sense of how big meters, centimeters, millimeters, and so forth were by measuring a bunch of different things, right? In particular, one of the measurements that I find to be quite useful is the one you did from the doorknob down. Do you remember about what that was? 94 centimeters, which is awfully close to 100, right, Lauren? And what is 100 centimeters? 1 meter. So that one is, it's not actually done on this next slide. This is a different version of it. But that to me is one that sticks in my mind. I remember doorknob down because I can see it. I go to doorknobs every day, right? They're everywhere. I see doorknobs and down. I know that that's about a meter. So to me, that's a common measurement that I have sort of stuck in my head. There's some other ones on here to help you out as well. So if you measure from your shoulder to the tip of your hand, this is going to be about a meter. Now, of course, it's not perfect, right? Because, well, probably everyone in this room, because Brendan's not here today, are probably pretty close to the same measurement from tip to shoulder. But if we had Brendan, or if we had my husband in here, my husband has these crazy long arms, it wouldn't make perfect sense, right? So this is an example of an approximation to keep in your mind. And you always have your shoulder and your arm, so you can have that in your mind as you're thinking about the length of a meter. A centimeter, so you got your finger, right? Those are always with you too, just in case you weren't sure. So the width of your fingertip is about a centimeter, okay? So if somebody talks about something in centimeters, you can kind of think, yes, that makes sense, or no, it doesn't, because you've got that measurement in your mind. And then you all know what a paper clip looks like. I've got them up here. I've got a whole drawer full of them right here. The tiny end of it, right, is about 1 millimeter. This the width of it is. The width of it is actually about a millimeter. And this is a common enough object that it's tiny, right? This is a common enough object that if you think about millimeter, you should be able to think about this and say, I know about what that looks like, because I know what a paperclip looks like, right? Okay, so the same kind of idea is true when you're looking at any of these measurements, and we'll talk about some more of them too. Like I gave you an example of the one last time that's absolutely, will always be stuck in my mind when I watched a student teacher who told me she had a 4-gram bird. And it wasn't her, right? It was her book. It was a terrible question from the book, but she just used it and didn't think about it, right? 4-gram bird doesn't exist because we just learned last time that a nickel's 5 grams. Okay, so yeah, not so good. So those are the kinds of things that we will have as sort of baseline estimations for ourselves to try to remember these as we keep working our way through. All right, so we're going to do a few conversions, and you guys know how to do these, so I'm going to let you do them. We are not doing dimensional analysis because there's no need. This is metric. Metric system means we move decimals left and right. So if it helps you, do you remember what we did last time on the very front of the board? We wrote some letters out. We talked about Henry dying, right? King Henry died by drinking chocolate milk. Or we can say King Henry doesn't mind drinking chocolate milk, was one with M for meters. So here was our chart, and we're moving things left and right between each of these. So give each of these 3 a try. We'll make sure everybody has the same answer after you're done with moving decimals. When you're done, just set your pencil down so that I know who's still working and who's finished. Okay, we're awfully close. Grab somebody next to you and see if you have the same answers as them. Just check, and if you differ, see if you can figure out what went wrong and on whose paper. Meters is the base.
Oh man,
Yeah.
I did it wrong.
It's okay. But you figured out that you did it wrong. That's good, Morgan. That's good. Okay, let's make sure everybody's on the same track. If we go from kilometers, km, into meters, how many places do we move? 3. Which direction? To the right. So which way will my direction of my decimal move? To the right. 3 decimal places. Well, there's only 2 that are listed there. So if I write 168, that's only moved 2 decimal places. So what do I need? I need to add a 0. So this is 1,680 meters. All right, millimeters to meters. How many locations do I need to move? Places do I need to move for that one? 3. Which direction? Left. 3 to the left. So if I move it 3 to the left, I end up with a decimal point and then 973. Agreed? Fantastic. And then on number 6, kilometers to centimeters. Woo! It's a big move, isn't it? How many steps does that take to move? 5. To the right or to the left? To the right. So if I move it like this, that's 2 to the right, right? And then I need 3 zeros. And I'll go ahead and write centimeters on this one since I don't have a blank to put it in, right? Yeah. And I think that took us, I don't know, a minute to do all 3 of those. It took us more than a minute to do all 3 of the other ones. Quite a bit more than that, actually. These are so friendly. Okay, fantastic. A couple other things in this section to be aware of. Triangle inequality. So this is talking about triangles. It seems like this could have appeared when we were talking about triangles before. We were looking at congruency relationships though, so perhaps that's why it didn't. The sum of the measures of any two sides of a triangle must be greater than the measure of the third side. And if you think about it, that should make sense. So let's actually put 3 points in space. Say they're these 3 points. And the longest side is the one that I'm kind of referencing. So I'm going to connect what appears to be the longest side. It would probably be that one. Agreed? And you've all heard the phrase before that says something like this. The shortest distance between 2 points is a straight line. Correct? So in order to get from, we'll label them, A to B, the shortest way to get there had better be that straight line. Which means that if instead of going straight from A to B, I went from A to C, and then from C to B, that better take farther to go, more steps, longer distance. And that's all the triangle inequality is saying. If I go through another point, it's going to take me longer. Everybody with me? Okay, so what we're going to do with the two examples they give us is we're going to decide if those measurements that they give us could in fact be sides of a triangle. That is, do they satisfy this condition that we are now sort of being made aware of, that we knew but we didn't think about before. 5, 7, 13. What do you think?
No.
No. What's wrong with it? Jamie, I saw you first. What did you see?
5 and 7. It's 12.
Right. 5 plus 7 is 12. And 12 is less than, is what I meant to say, less than 13. Right? So this is a no. Absolutely can't work because 2 of those sides is not longer than the third. How about the next one, 5, 8, 13? No, because what happens when I do 5 plus 8? It actually equals 13. Has to be greater. Exactly.
Wait, well why is that one no, that one's not bigger than 13?
I know. They're both not bigger than 13. I need this to say greater than, and they are less than, and they are equal to.
Oh, duh.
Yeah.
Okay.
The other symbol. Yeah, so these don't work, right? They don't work. If you were trying to put a triangle together like this, like we've tried putting triangles together. So when we did construction of triangles, you had 3 side lengths, and you never worried. You just knew they were going to work out because I gave them to you. What I gave them to you was all going to be fine, right? But what if they had given you some triangle lengths that didn't work? What would happen? Well, what would have happened is you would have gotten one side length of a triangle, and you've gotten others that look something like this. Can't make a triangle. The other 2 segments are too short, right? Or what you might have gotten is you might have gotten this piece right here. I mean, it might have been really close, which would have been like the last example that we just did. They're really close. And in fact, you might think, okay, well, maybe I just make the angle smaller until it works. Well, you know what happens if you make the angle small enough for it to work? It collapses to itself. Straight line segments, not going to work. Okay, so that's what the triangle inequality is referring to. Okay, a few more things in this section. Perimeter. Who's heard of perimeter before? All of you have, okay. So perimeter, we're going to talk about first of a simple closed curve. This is the length of the curve. Okay, just the length of the curve. Polygons is what we usually do this for, though. So of a polygon is the sum of the side lengths, or sometimes you'll hear it called the distance around the polygon. We kind of use those interchangeably because, of course, they mean the same thing. Perimeter. So you have an example. Find the perimeter of this triangle. Don't spoil the fun for anybody else. Find it, write it down, and we'll make sure everybody got it. What's the perimeter of this triangle? 30 centimeters, right? So if I add, 8 plus 10 plus 12, I get 30. And again, we're making very sure and careful throughout our work that we're using our units. This is 30 centimeters. All right, so if we have a polygon, remember polygons are these straight, flat-sided objects. We've been working with them a lot this semester. We just add up the side lengths, and then we have the perimeter of our polygon. A very special kind of perimeter is one called circumference. Circumference is really the perimeter of a circle. And it's so special that it gets its own letter, capital C, for circumference. So a few features about a circle in relation to its circumference. Radius is the distance from the center of the circle to the circle's edge, and that's in blue in my picture. It's labeled on your paper as well. It's denoted R, letter R. The diameter is the distance from edge to edge, but it has to go through the center. We denote it D. And notice, really what it is it's the radius twice. So the diameter equals 2R. D equals 2R. And then you've probably heard somewhere along the way, the last piece here about pi, but you might not have heard it referenced in quite this way. Pi is actually a ratio of the circumference to the diameter. So ratio, remember, means fraction. It's a relationship in a fractional form. So if we wrote the circumference on top, the diameter on bottom, and we did that division, we would end up with the value pi. Okay? And I actually have, I don't have it with me today, but I'll bring it next time, a book to read you that uses this information, and it's very, very clever. Okay, a reading book. We read the tessellation one before, right? I have another one. I like it even better than the tessellation one. So I'll show you that one. Hopefully next time we'll have some time for it. And then a couple of formulas that has these relationships. Circumference is equal to pi times the diameter, and that's fine. We can use that. But the one that we tend to use more often is probably that circumference equals 2 pi r. So 2 times pi times the radius. And of course, you'll see that this formula right here for diameter equals 2r is exactly present in this formula here where you've got the 2 and the r there, right? That's where that's coming from, is the relationship of all these together. One more formula, and this one you may not have seen in a while. It's not as lower level, like elementary level kind of stuff. This stuff you're going to see no later than 6th grade, because I've seen my student teachers in 6th grade using this in classrooms, so no later than 6th grade. This piece is probably going to not be 6th grade, a little bit higher. This is called arc length. So in order to talk about arc length, we have to talk about a central angle. So a central angle is an angle whose vertex is at the center, hence the word central, center of a circle, and whose sides are radii of the circle. And radii is just plural for radius, right? Syllabi, syllabus, that kind of stuff. So radii, 2 radii meeting at the center of the circle create a central angle. And then the arc length is the red piece that's along the outside. So imagine a pizza, okay? How big the angle of the pizza is really what you're looking at when you usually select that slice of pizza. And the arc length is the crust part. Okay, it's the outside edge of the crust part. The angle measurement, the formula for arc length is pi r theta over 180. And I want to show you where that's coming from because it's really not anything mysterious. It looks a little bit like funky. But it's something that you should be able to figure out. If you forgot this formula, you should be able to figure out what it is because of the relationship. What is the formula for the circumference? We just did on the previous slide. What was it? Yeah. So the circumference formula was
2 pi r, sorry.
2 pi r. Yeah, not radius squared. That one's going to be area, which we will do soon. But 2 pi r. Now, that would measure the crust all the way around the pizza, right? But we just want it around the one slice. So what do we have to do? Well, it's going to be dependent upon how much of the pizza it is, right? If I have a quarter of the pizza or if I have 3/4 of the pizza, that will change my arc on the outside, my crust length. So how do I make that decision? Well, what I do is I multiply it by how much my angle measurement is compared to the whole angle of the circle, which was 360. Right? It's a ratio. It's the percentage or the proportion that I have of the whole pie. Well, you'll notice, though, if I multiply these, here's a 2 over here, and there's a 360 on bottom, and they're both even, right? I can reduce those. So I can mark out the 2, I can divide the 360 by 2, and I get 180. And lo and behold, that's the formula that's written above. Pi times r times theta over 180. That's where it's coming from. Just a proportion or a percentage of the circumference formula. And this would determine how much of the crust you have, the arc length, something like that. So we're going to do an example of a couple of these. Are you ready? Morgan, you look terribly confused.
Yeah,
Can I help
I'm
you with
really
something?
confused. I'm a little confused why the 2 and the 360 got canceled.
Because they're both even, and I just divided them both by 2.
Oh.
Just reduced like you would reduce a fraction.
Okay.
That's all. My goal was that I wanted to show you where the 180 came from is why, actually.
Oh, yes.
Because that's where it's in the formula, it's the 180. Is there any other questions about the formula or where pieces of it are coming from? Okay, let's try some examples. We've got a couple of them here. One you have on this page. It says a circle has a diameter of 4/pi centimeters. What is its circumference? So the first thing we need to do is we need to write down or think about, whether we're writing it down or thinking about it, I don't care, but we need to think about the circumference formula. So what is the circumference formula that has diameter in it? I might as well use the diameter formula because I've got that information. Pi times d, right? And then the information in this particular problem is, in fact, the d of this formula. So it's pi times 4/pi. And that gives me what? 4. Yeah. Beautiful things happen when the numerator and the denominator both have the same value in them. They cancel, right? So this is just 4. 4 what? Centimeters. And I need that, right? Yes, Dr. Hans, of course. Absolutely. You bet. Yes, we do. Okay, 9 on the next page of yours. If a circle has a circumference of 0.68 meters, what is its radius? So now I need a formula that relates circumference and radius. Okay, what's the formula that relates circumference and radius? Circumference equals 2 pi r. I know it's not solved for r equals, but does it matter? No, it doesn't matter at all. We can plug in numbers on either side of this equation and solve for the other side. So I'm actually told circumference this time, so I'll fill in the 0.68 on the left. 2 is a number, pi is a number, and r is what I do not know on the right. So what would I have to do now to solve for r? Divide by 2 pi. Now you need to be really careful with your calculators when you divide by 2 pi. Because there is a very good chance if you enter this as 0.68 division 2 times pi, that it will not divide by pi. It will multiply by pi because it's going to move from left to right. So be really careful. Most of your calculators, and I'm not going to say all because I don't know what all calculators y'all have, but most of your calculators want you to put a parenthesis around the 2 times pi in the denominator in order to make it very clear to it the order of what you are expecting it to do in order of operations. Okay? The other thing you can do is you could do 0.68 divide by 2, hit enter, divide by pi, hit enter, and then you don't have to worry about any parentheses. And that's a way to do it too. Just a 2-step process. All right, so I mentioned earlier today we're going to go with 2 decimals when we have to approximate, and I'm just sure we're going to need an approximation here. So if we approximate this, what do you get for your radius? 0.11, and Ashley said meters. Do we agree? Yes? Okay.
Well,
Awesome.
rounding.
We're going to round to 2 decimal places.
Okay, because I got 0.108.
Yes.
Okay.
108, and the 8 would round the 0 up to a 1. Exactly. Yep. Okay. All good? Fantastic. Oh my goodness. 2 more, and we're done with this section. We have time to finish it, but we won't do group work, so we'll talk about that here in just a second. Let's finish for now, and then we'll talk. This one wants us to find something about a semicircular arc of a circle whose radius is 1/2. So I'm hearing the word arc, and I want to find a length. That sounds like I'm probably going to use arc length. Agreed? Okay. Arc length had a formula, and oddly enough, I didn't write it in here because I don't think your book probably has it, but usually arc length uses the letter S. It's probably something in Latin. That would be my guess. That's usually what happens when we have letters that show up in weird places in mathematics that don't seem to matter or don't seem to make sense. The formula, though, wait, no, maybe it did. Did it have L? Your book did have L. I take it back. I remember now. Your book did have L. S is what I see in my other textbooks for this one. Okay. And the formula was what? Had a pi in it, and then what? Pi r theta over 180. 180 degrees. What information do I know? Tell me something I can plug in. I've got my pi. What's next? 1/2. So either put in 0.5 or 1 over 2. I've got my 180 in the denominator. What in the world is theta? It's the angle, the central angle for the arc length.
Is it 180?
It's 180. Why is it 180, Catherine?
Because it's a semicircle and that's half of the...
Right. So if I were to have a circle here, and I were talking about a semicircle, then the angle measure here would be 180 degrees.
It's the line that goes.
Yeah. Also known as a diameter, right? Yeah. So its angle measure of this line would be the angle measure of 180 degrees. It's also called a straight angle. I know it's been ages since we did that. Beautiful things, though. Look at that 180. That was friendly. So now we just have 0.5 times pi. And again, we're going to put our answer in decimals because most of what we're doing has practical applications. And if you go telling somebody that the length is 0.5 pi, they're going to look at you like you lost your marbles, right? They're going to be like, what do you mean? So what is this with decimal representation? 1.57, and units would be inches. You got it. 1.57 inches. Last one says, what is the radius of an arc whose central angle is 82 degrees and whose arc length is 160 centimeters? So same formula as last time. But what information do I get to fill in this time? I get to fill in L. What does L equal?
160.
160, because it said the arc length is 160. Pi is a number. What's R? We don't know. That's what we're looking for, correct? Yep. What about theta? 82. And then I've got the over 180, right? Those are both degrees. There's several things you could do. My suggestion would be to multiply by the 180 first, just so that we get rid of the fraction more than anything, really. The 180 cancels. What do you get when you multiply 180 times 160?
28,800.
I've got 28,800 on the left, and I have pi, r, and 82 on the right. The degrees actually cancel because there are degrees on the top and the bottom that are working in our favor here, if you want to think about it that way. What do I need to do next?
Divide by 82.
Divide by 82, and I'll divide by 82 pi. If you want to divide by 82, hit enter, and then divide by pi to avoid the parenthesis issue we talked about before. That's totally cool. So what is 28,800 divided by 82 pi?
111.8.
Okay, and we'll use two decimals, so 111 point.
It's 0.79.
Okay, so 80 then, right? Yeah, so 79 and then it's something bigger, so that's why you round it up to an 8, and we'll put the 0 as a placeholder in the hundredths place. Units? Centimeters. Centimeters. I think our clock is almost on time now. It's actually just a touch behind. Interesting.